Look at this exercise. Saying, what are the largest and the smallest resistance you can obtain by connecting 36 ohms and 50 ohms and a 700 ohm resistors together? So what is the largest resistance? What is the smallest resistance you can obtain by connecting all these resistors together? Well, when you get the largest resistance is when resistors are connected in series. So that means that my largest resistance is R1 plus R2 plus R3, which is 36.0 ohm plus 50.0 ohms plus 700 ohms, which is going to be 786 ohms. And this is the largest resistance. Now, the smallest resistance is when the resistors are in parallel. Where 1 over the equivalent resistance would be 1 over R1 plus 1 over R2 plus 1 over R3. There is one way to rewrite this equation. There is, let me show you quickly this. You can just get this equation and you multiply by R1 times R2. So sorry, you have R1 here in the denominator, multiplied by R2, R3. And you multiply above by R2, R3. Now, in the second equation, you have R2, so you multiply by R1 and by R3 this one. And you multiply here above by R1 and R3. And in the third equation, you have R3, so you multiply by R1 and R2. So you multiply by R1 and R2 over here. What happens? Now you have that 1 over the equivalent resistance is R2, R3 over R1, R2, R3 plus R1, R3 over R1, R2, R3 plus R1, R2, R2, R3 plus R1, R2 over R1, R2, R3. So I just found least common denominator R1, R2, R3. You know, and now I have the same denominator, so I can say that this is R1, R2, R3, and then this is R2, R3 plus R1, R3 plus R1, R sub 2. Now we can flip both sides, and we can get that the equivalent resistance is R1 times R2 times R3 over R2, R3 plus R1, R3 plus R1, R sub 2. When I substitute now, I say R1 times R2 times R3 is 36 ohm times 50 ohms times 700 ohms, all divided by R2 times R3 is 50 ohms times 700 ohms plus R1 times R3 is 36 ohms, 700 ohms plus R1 times R2 is 36 ohms times 50 ohms. When you resolve that, you will get that this is 20.32 ohms or 20.3 ohms. And that is the smallest resistance between those three resistors. That is the smallest resistance between those resistors. So always the largest resistance will be connecting the resistors in series. And the smallest resistance is when you connect the resistors in parallel. Always. Okay? Now, let us solve another exercise. My next exercise will be this one. I would like to highlight something. The equivalent resistance of the resistors in series is always larger than the resistance of the larger resistor. So the largest resistor has 700 ohms. Your equivalent resistance was 786 ohms. So always the equivalent resistance in series is larger than the resistance of the resistor with the largest resistance. Now, the equivalent resistance in parallel is always smaller than the resistance of the resistor with the smallest resistance. So always this equivalent resistance in parallel is lower than the resistance of the resistor with the lower resistance. In this case, the resistor with the lower resistance is 36. So if you find that resistance in parallel, you know you have to get a number less than 36. If you get greater than 36, you did something wrong. Now let's see this other problem. They say, just consider the circuit below. The terminal voltage of the battery is 18 volts. Find the equivalent resistance of the circuit. Find the current through each resistor. Find the potential drop across each resistor. And find the power dissipated by each resistor. And find the power supplied by the battery. So first they are asking this, find the equivalent resistance of the circuit. These resistors are in series. So if I want to find the equivalent resistance, it will be R1 plus R2 plus R3. So it will be 4 ohms plus 1 ohm plus 4 ohms. So this equivalent resistance will be 9 ohms. So here we have the equivalent resistance of this circuit, right? Oh, this is a series connection. That's why we found the equivalent resistance like that. What did the next they ask you to do? They say find the current to each resistor. The current to each resistor is the same, because here we have just one current that flows through the circuit, because there is only one loop. So you have a current I leaving the battery, passing through this resistor, passing through this other resistor, passing through this other resistor, and coming back to the battery. And it's always the same current, because there is only one loop. So if I want to find that equivalent resistance, that current will be by Ohm's law, the voltage divided by the resistance. What resistance? The equivalent resistance. So this current will be the 18 volts of the battery divided by the 9 ohms divided by the 9 ohms. That is the equivalent resistance. So this would be 2 amperes. Let's use a number of significant figures. So let's say 2.00 amperes. That means now current to 1 is equal to the current to the resistor 2 and is equal to the current to the resistor 3 and is equal to I and is equal to 2.00 amperes. So the current to all the resistors is the same. Now, they want you to find the variation of voltage across the resistors. So what we know that there will be to the resistor a delta V1, to the resistor 2, V1, to the resistor 2, there should be a delta V2, a drop of voltage, and to this other resistor there should be a delta V3, another variation of voltage, right? And what else are we expecting? We're expecting, right? And this is important. We're expecting that the voltage of the battery will be equal to the sum of the variation of voltage across the resistors. So we're expecting that. Now, how do you find this variation of voltage across the resistors? You know by Ohm's law that current is voltage divided by resistance. So, if you solve for voltage, you know that voltage is current times resistance. So, if I want to find delta V1, the variation of voltage across the resistor 1, this would be the current I times the resistance of the resistor 1. So, it would be, what is the current I? 2 amperes times 4 ohms. So delta V1 would be 2 times 4, 8 volts. Delta V2 is I times R sub 2, which is 2 amperes times 1 ohm, because R sub 2 is only 1 ohm. So delta V2 would be 2.00 volts. Delta V3 is I times R sub 3. So it's 2.00 amperes times 4.00 ohms. So again, delta V3 is 2 times 4, 8.00 volts. Let's see if it's true. B, the voltage of the battery is 18 volts. The question is equal to the sum of the drop of voltage. I have 8 volts plus 2 volts plus 8 volts. So I got that 18 volts is equal to 18 volts, which is okay. This is what is expected. So like that, we calculate the variation of voltage across each resistor. What they ask you next, they say, find the power dissipated by each resistor. the power dissipated by each resistor. To find the power dissipated by each resistor, you can multiply the square of the current times the resistance of the resistor. So the power dissipated at resistor 1 will be the square of the current times the resistance of the resistor 1. Because this is what power is. So the power to 1 would be the current, that is 2 amperes, squared times 4 ohms. So the power to resistor 1 dissipated by the resistor 1 is 16 watts. Because 2 squared is 4 times 4, 16. But the unit of power is watt. Now the power dissipated at resistor 2 is the square of the current times the resistance of the resistor 2. So P2 is 2 amperes squared times 1 ohm. 2 squared is 4 times 1, it's going to be 4 watts. The power dissipated at resistor 3 is I squared times R sub 3, which is I squared, 2 amperes squared, and the resistance of the resistor 3, which is 4 ohms. So this power is equal to, again, 16 ohms, 16 watts, sorry. So again, 16 ohms, 16 watts, sorry. So there we have the power dissipated at each resistor. Finally, they say find the power supplied by the battery. And the power supplied by the battery will be equal to the product of the current times the voltage of the battery. The power supplied by the battery will be the product of the current times the voltage of the battery. So this power will be the current of 2 amperes times the voltage of 18 volts. So the power is 36 watts. Now, let's do something quickly. Let's add the values of power dissipated by the resistors. 16 watts plus 4 watts, 20 watts. Plus 16 watts, 36 watts. So 36 watts were dissipated. Right? Now, 36 watts were provided by the battery. So I have the same number of watts dissipated than the number of watts provided by the battery. Now, the next exercise I want to show you is an exercise, and we take a little time, from the lab just to explain like 2 more exercises, right? Now, the next exercise I want to show you is this exercise. This is a Kirchhoff problem. This is a Kirchhoff problem. I don't show here the circuit. Each resistor. Now, what I'm going to solve for this exercise, I will calculate the currents using Kirchhoff. Now we know how to calculate power dissipated, power consumed, power supply. So, how is my circuit? The circuit would be like this. The circuit, we have a battery here. Then there will be one junction here with one resistor that is R sub 1. And R sub 1 is 2 kilo ohms. And then there will be here another battery. And then we will have here another junction with another resistor here. And there will be another resistor here. This resistor is R sub 2 and is equal to 1 kilo ohm. And this one is R sub 3 and is equal to 1 kilo ohm. Now, this battery have 1.4 volts. And this other battery over here, we will call battery 1, have 1.6 volts. 1.6 volts. So this is my circuit. Now, we're going to calculate the currents because we have solved some exercise before where we have done power dissipated, and power supply. So what are we going to do is calculate the currents. Well, I should have here basically three currents. I will call the current passing through R1, R sub 1. I sub 1. I will be assuming that it's in this direction. Why? Because based on the polarity of this battery and the polarity of this other battery, the current in both needs to be flowing like this. Now, I will have another current here that I will call I sub 3 that pass through the resistor 3. And I will have another current here that I will call I sub 2 and pass through resistor 2. Okay? Now, I have then one junction over here, and I will apply the junction rule to this junction. Now, based on the junction rule, we have I1 enters into the junction, and I2 and I3 are leaving the junction. So that means that I sub 1 minus I sub 2 minus I sub 3 is equal to 0. And this is junction rule applied to the junction that I highlight in red. I sub 1 enters into the junction, that's why I put that positive. I2 and I3 are leaving the junction, that's why I put that negative. Now, I have three loops. I have one small loop over here. I have another small loop over here. And I have one big loop, all this way here. So I will really take one loop that would be my loop one, that would be this one. And I will take another loop that will be this one. So this will be loop one and loop two. When I take these two loops, I'm sure that I will pass through all the devices connected in my circuit. I will include in at least one loop all the devices connected. Now, when we apply the loop rules, we have to be clear of the signs. So when you pass through a battery, you go from negative to positive, right? When the current goes from negative to positive, you have a positive voltage. When you pass through a resistors in the direction of the current, you will have a negative drop of voltage. So that means that I will have here what? First, V1 positive, because I am going in this clockwise direction in loop 1. So we have V1 positive, and now I pass through R1 in the direction of the current I1, so I say minus I1 times R sub 1. And I pass through R2 in the direction of the flow of current, so I say minus I2 R sub 2. And that is equal to 0. Loop rule, right, for loop number 1. Now, I'm going to do the same for loop number 2. If I apply now my loop rule like this, look at this. I will go to V2 from positive to negative. So we have minus V2. I will pass through R sub 3 against the direction of the current because I am just taking the loop clockwise. So when I go from negative to positive across my resistor, I have an increasing potential. So I say plus I3R3, plus I3R3, and then when I pass through R1, again I pass against the direction of the current I sub 1, so I have plus I1 R sub 1. And this is another loop. Now what happens? You will substitute now the resistance by their values. And you have a system of equations with 3 equations and 3 unknowns. So you have one equation that would be I1 minus I2 minus I3 equals 0. Then later you have one equation that is R sub 1. This is in kilo ohms, right? When you work in kilo ohms, you can work in kilo ohms, but your answers are going to be milliamperes. You work in kilo ohms. Otherwise, you can just work in ohms, and it's very less confusing. So we work in ohms. So that means that I say B1 here is 1.6 volts. I will not use the units because if not, it's going to turn very confusing. Minus I1 R sub 1. R sub 1 is 2 kilo ohms, so it's 2,000 ohms times I1 minus Then I2 R2, there is 1000 ohms times I2. Well, this is equal to C. And I have another equation that is negative V2, so it's negative 1.4 plus I3 R3. So R3, the resistor 3 is 1 kilo ohm, so it's 1000 ohms, and I sub 3 plus I1 R1. So I have R1 is 2000, so plus 2000 ohms, times I sub 1. And all this is equal to 0. Now, let's do something. Let's reorganize the terms to get a system of equations. So you say I1 minus I2 minus I3 is equal to 0. Now, negative 2000 I1 minus 1000 I2 is equal to minus 1.6. Because I subtract 1.6. So the constant goes to the right. And then I say 1000 I3 plus 2000 I1 is equal to 1.4. You can multiply this equation by negative 1, so you get rid of all these negative signs. You can say I1 minus I2 minus I3 equals 0. 2000 I1 minus 1000 I2, sorry, plus 1000 I2, because you will multiply everything times negative 1, is equal to 1.6. And later you say, reorganizing this a little bit, 2000 I1 plus 1000 I3 is equal to 1.4. Now, this is a system of 3 equations with 3 unknowns. In Coles Algebra 1, we explain how to solve systems of equation by elimination and substitution. But it's going to be extremely large, the procedure. So in Coles Algebra 2, you probably learn the determinants and the Cramer's rule. I don't know if you have listened to this. Cramer's rule and determinants. Determinants D. It's easier to calculate determinants here. There are softwares, there are web page that calculate the determinants. So you have just to enter the values on the matrix and they calculate the determinant. So how, just trying to go back to your knowledge of Coles Algebra 2, I will apply the Cramer rule. And I will say that determinant D will be the matrix that contains the values 1, minus 1, and minus 1 are the coefficients of this first equation. Then minus 2000, minus 1000, and 0. And then, sorry, no, positive 2000 and positive 1000, because I already changed the signs. So it's positive 2000, positive 1000, and 0. And then the other one is 2000, 0, and 1000. When you calculate this determinant is equal to 5 times 10 to the 6. Later, you have to calculate the determinant D1. In D1, you change the first column by the numbers to the right of the equal sign, right? So your first column becomes 0, 1.6, and 1.4, and the other two columns stay like that. So -1, -1, 1,000, and 0, 0, and 1,000. When you calculate that determinant, you get 3 times 10 to the third. Later, we calculate the determinant D sub 2. D2, you change this column by these constants. So the first column stays like that, 1, 2,000, and 2,000. The second column becomes 0, 1.6, and 1.4. And the third column becomes now, or stay like -1, 0, and 1,000. And when you calculate this determinant, it gives you 2 times 10 to the third. And then finally, we calculate D3. And the determinant D3, you will keep the first two columns of D, and later you will change the third column by the constants. So we say 1, 2,000, and 2,000. 1, 2,000, and 2,000. -1, 1,000, and 0. And then 0, 1.6, and 1.4. And when you calculate the determinant, you get 1 times 10 to the third. Now, current 1 is D1 over D. So it's 3 times 10 to the third divided by 5 times 10 to the 6. So current I1 will be approximately 0.6 times 10 to the -6 amperes, or 0.6 milliamperes. Current 2 would be D2 over D. So it's 2 times 10 to the third over 5 times 10 to the 6, which is going to be 0.4 times 10 to the -6 amperes, or 0.4 milliamperes. And I3 would be D3 over D, which is 1 times 10 to the third divided by 5 times 10 to the 6, which is 0.2 times 10 to the -6 amperes, or 0.2 milliamperes. And there I have the values of the currents that pass through the resistors. This is what is Kirchhoff law. This is how you solve a problem using the Kirchhoff rules or Kirchhoff law. Now, you don't have to use determinants. I don't know if you remember the determinants and the Camel rule from college algebra 2, because I don't know, how many terms ago you took the college algebra 2. But your instructor of college algebra 2 was supposed to explain Camel rule and determinants, right? So this is easier than doing it by substitution or by elimination. But yes, we can also do it by substitution and by elimination, and it's not going to be a good problem. I mean, when we're here, when we have the equation, the three equation with the three unknowns, you can do it by substitution or elimination. It doesn't matter. It's going to work. But the determinants, there is one way to that means there are a lot of applications that evaluate determinants. Even the calculators do that. It is easier. Some calculators do it. It's easy. So that's why I always prefer to use the determinants when I have to do those many calculations, right? So this is an example of using Kirchhoff rules. Now, of course, in the exam, well, Kirchhoff maybe is not a good idea because it's too long, right? It takes too much time.
Are we going to be allowed to use calculators?
Huh?
Are we going to be allowed to use calculators?
Yes, scientific, yes, absolutely. Yeah. No, there is no way.
Do we have to bring our own?
Yeah, you sure, yeah. To bring your own, is it?
Yeah.
Yeah.
Or do you have?
I have some. I have like a tree, but I don't know if.
Yeah.
So let's see now another example. And this one is now one example about an RC circuit, just to finish, with this part. So what is this example? They say a 500 ohm resistor and on charge 1.50 microfarad capacitor and a 6.16 volts electromotive force are connected in series. So they say, what is the initial current? Hello. What is the RC time constant? What is the current after one time constant? What is the voltage on the capacitor after one time constant? Right? Now we know what the time constant is, right? It's the product of the resistance and the capacitance, right? So the first they ask you is to calculate the current. So I have a resistor of 500 ohms. I have a capacitor of 1.50 times 10 to the negative 6 farads. And I have a power source of 6.16 volts. And the first is to calculate the initial current. The initial current, I sub 0, right, is equal to the voltage of the source, of the power source, divided by the resistor, based on the Ohm's law. So we are going to divide the 6.16 volts by 500 ohms. So the initial current would be 0.01232 amperes, which is going to be approximately 12.3 milliamperes. So that is my initial current. Second, they say calculated time constant. The time constant tau is equals to RC. So we multiply the capacitor times the resistor. So tau will be R is 500 ohms. And C is 1.50 times 10 to the negative 6 farads. So tau, the time constant in seconds, would be 750 times 10 to the negative 6 seconds. (750 times 10 to the negative 6 seconds. And in scientific notation would be 7.50 times 10 to the negative 4 seconds. Or it would be 0.75 milliseconds. Right? This is tau, but tau is better to have in seconds. Do you remember in the experiment that I did, how was my tau? My time constant was 43 seconds in my experiment. Why? Well, first, I was using a very, very high resistance because I had two resistors of 4,700 ohms each. 4,700 ohms. No, 47,100 ohms and 47,000 ohms. So I had in total 94,000 ohms. They had only 500 ohms. But also, my capacitor was a capacitor of 470 microfarads. And they are using a capacitor of only 1.50 microfarads. So they are using, or they have an RC circuit with a very small resistance and a very small capacitance. So that's why the time constant is that small. So for such a time constant, we cannot appreciate the variation with the voltmeter. That's why I use in the experiment those high values of capacitance and resistance, because like that my time constant was 40 something seconds, and we have no chance to see the variation of the voltage in the voltmeter. But with this time constant, there is no way to see anything. It's very small. Now, after the time is constant, they say, what is the current after one time constant? Well, the equation of the current is I sub t is I sub 0 times e to the power of negative t over tau. This is the current. I sub 0 times e to the power of negative t over tau. Now, when t is one time constant, after one time constant, means that the time t is equal to tau. So, I of tau is equal to I sub 0 times e to the power of negative tau over tau. So this would be I of tau, I sub 0 times e. I of tau, I sub 0 times e to the power of negative 1. So this would be I sub 0 over e. So after one time constant, my current will be I sub 0, that is 12.3 milliamperes, divided by E, the Euler's number, the natural base that we learned in Coles algebra. So I of tau, the current after one time constant, would be 4.53 milliamperes. 4.53 milliamperes. Now, next, they say, what is the voltage on the capacitor after one time constant? Or is discharging the capacitor? So again, the voltage across the capacitor would be E times 1 minus E to the power of negative t over tau. Now again, the voltage after one time constant we know we have 62.3% of the initial voltage, right? So T is equal to tau. So the voltage in the capacitor in one time constant is E times 1 minus E to the power of negative tau over tau again, which is negative 1. V sub C tau of tau would be E 1 minus 1 over E. Right? So this would be the voltage in the capacitor after one time constant. It would be E, which is 6.16 volts, because it's the electromotive force. 6.16 volts times 1 minus 1 over E. Remember that is the Euler's number, 2.78, blah, blah, blah. So we see voltage in the capacitor at one time constant. When you calculate that, you get 3.89 volts. Because it should be 62.3%, this 3.89 volts must be the 62.3% of the electromotive force. You know? Remember that always after one time constant, you have during the charge 62.3% of whatever other magnitude you have. And there's a size number.